To check what happens about unitarity, let us recall the consequence of the optical theorem that we would like to confirm. And the optical theorem tells you that the imaginary part of the bubble diagram times minus I, which is the imaginary part of the amplitude, actually there is an I between what you call amplitude and the Feynman diagram, is equal to something positive, where this is the integral of the phase space of the final states, because basically you are cutting this diagram, and the loop integral here, when you take the imaginary part, converts into the integral of the final states. So there is an integral of the final states, but actually, if you recall the equation, there is also a sum that is a completeness relation. So you see what's in between has a sum. So there is a sum here. Here, why did I say that there is a sum? Now we check. Well, the moral of the story is that if you come from above or from below, you have an imaginary part. And the imaginary, that discontinuity is the difference between what you get from above and from below. So the difference cancels that, but that will be a delta function which puts you on shell. That's why you get a physical process. But that would be, in this case, a physical process with imaginary masses, so it would be an unphysical process. However, when your amplitude is given by the arithmetic average, it's real, and there is no imaginary part. That means that this is 0. So that should be equal to 0. And that is easy to achieve, because you just have to declare that those states are not in the spectrum. You just exclude your final states from the spectrum, and you have to restrict the sum of f of states over states in the spectrum. So now you have your unitarity equation, because you can have unitarity equation in the full space W, because in general that's what you get. It's an equation with a plus or minus sign depending on well, the plus or minus sign is with a Feynman prescription, which means that you reach from above. Every branch cut is reached from above. But you have a second possibility, that these states n get a factor 0, not an exponent 0, which means that you can just drop them out of the spectrum. So you will have that the it is correct, this equation will be correct if you restrict the space on which you take the sum to the subspace that doesn't contain these states. Because in that case, when you remember, you have this general equation which is valid for t, and then you translate it into a diagrammatic equation. But in this case, the diagrammatic equation would tell you that the imaginary part of the bubble diagram has to be 0, because there is no state belonging to V. If your bubble diagram has here a certain state with imaginary masses, then the diagrammatic equation would take those states with imaginary masses as final states. But you are just saying that those states as final states are in the big Fock space, they are not in the physical space, so you get the correct optical theorem in the subspace V. So again, if you have W, if you have here the sum over all W, the whole space W, this will be not true. So after using this prescription, you violate unitarity unless you make the projection. You are forced to make the projection. And the projection is this restriction from the complete Fock space to the subspace. And that means that these particles that propagate in this funny way, with this prescription, for example, you have this propagator, you either have a higher derivative theory, or you make it into a higher, or sort of a higher derivative theory, but by having denominators like that. But then you take epsilon going to 0 with the entire procedure, because this is a little bit naive. You cannot, still you do not know how to treat those regions. So you have to tell me when you can shrink them, okay, to branch cuts, but then what? Do you go from above? Do you go from below? Both will give a non-zero result here. And actually a non-zero result there, the imaginary part. Or you can take the average of the two, or which is equivalent to go inside and then make the deformation. So that completes the prescription, tells you how to compute the loop integrals, and then you say your physical space is a subspace of the Fock space, so you have. But this entire construction, precisely because these there is a projection, you throw these states away, works for both signs. And that's how you turn a ghost into a fake particle, and this is what I call a facon. With both signs, so there is a facon with plus and a minus, depending on this. You can quantize this way a propagator with the right sign or a propagator with the wrong sign. They are both fake. They have different physical implications. And you can imagine this fake particle as a particle that can only be virtual. It can only circulate inside diagrams. Here it is. but it cannot be in the physical spectrum, so it's not an asymptotic state. In some sense, it's like an auxiliary field. You integrate it out. But it is an auxiliary field with a kinetic term. And the kinetic term is what makes everything interesting, because normally auxiliary fields are just used for, they do not propagate. And this kind of propagates. It doesn't get to the external asymptotic states, but it does propagate. So for example, what do we do with the gravity? In gravity, if you start with, well, first we want renormalizability, so our theory will be a theory with higher derivatives. And I parameterize the action anew because I do not remember which parameters I used. And I write it this way. This combination is equivalent to the square of the Weil tensor apart from a total derivative. Zeta, alpha, and psi are positive. Cosmological constant is positive or negative. And there is a way to rewrite this action without higher derivatives by introducing extra fields. Basically, you write, for example, r squared with an auxiliary field phi. You can write it like that. Oh, phi squared. And then make some change of variables to diagonalize the resulting action if you introduce some auxiliary field. Well, in a non-higher derivative form, it's more explicit because here you have complicated higher derivative propagators. Instead, in a non-higher derivative form, you just have more fields, but with normal, so-called normal propagators. So let me write it. That is equal to, let me set the cosmological constant to 0 for simplicity. Otherwise, there is some redefinition, but this can be done anyway. So you have the Hilbert term for gravity. Then you have a scalar. With a potential and a certain mass. And then you have a spin 2 field the mass of the scalar is given by a combination of those parameters. You have a scalar field which has a funny potential but a right sign in front of the kinetic term. Instead you have S chi, which is not right here. It's an action of a spin 2 field. How do you know it is an action of a spin 2 field? Because it's a Pauli-Fierz action. You can work it out. It's a Pauli-Fierz action, which we know is a spin 2 field, with a certain mass. A non-minimal coupling and many other vertices in infinite tower of vertices, but that is not important. What's important is that this tilde is due to the cosmological constant, so let's eliminate the tilde. It has the wrong sign. So we are precisely in a situation like this. We will have the Pauli-Fierz propagator, but apart from indices and many funny things, the important thing, you will have a minus in front. And that means you have to quantize this. This is a symmetric tensor, by the way, so yes, chi mu, so it's a symmetric tensor because it's a Pauli-Fierz action. You need to quantize that as a fake particle. And project it away then. What about the scalar phi? The scalar phi is the right sign. Probably these masses could be large in nature. There is not just the Planck mass here, but there are 3 parameters. So the masses could be smaller than the Planck mass, which means that the effects of those 2 particles could be evident, testable even, who knows, well before reaching the Planck scale. But the scalar phi has the right sign in front. So will it have to be quantized as a true particle or a fake one? Both. Anytime now you have a choice, and every particle you can introduce to your standard model extension, for example, could be fake or not. There is some physical implication. Unitarity is okay. Renormalizability is okay, but there is some rethinking of space-time at small distances that we will see today or in 2 days. That is actually the interesting part, because when you talk about quantum gravity, you expect that you have to rethink space-time somehow. But here, we are deriving everything. We are not assuming what space-time is. Actually, it's very naive to assume that we can assume what space-time can be down there, as many approaches do, because actually they assume and they start from assumptions that are quite gratuitous. String theory, for example, looped quantum gravity, and every other approach assumes the nature of the change of the nature of space-time with no clue whatsoever. Here there is no assumption. We are just using particle physics, and we start from the standard model, apply the same rules, and there is a unique theory, which is this one. it is quantized in an essentially unique way because the fake particle has, the spin 2 has to be quantized as a fake particle. Phi can be quantized both ways, so actually you have two possibilities, but still essentially unique, let's say. You have a finite number of possibilities too, and a finite number of parameters. And the theory is predictive with, like the standard model. Phi could be real or fake. So two possibilities. And when we discuss the physical implications, we have to keep in mind that we have double possibilities. So you can ask yourselves now, what about the fields we have in the standard model? Are we sure that there are no fake particles? Well, we are not sure that all of them are not fake. Well, so we know that first of all, where to check. We know that the Facon prescription changes imaginary parts. Imaginary parts are what happens above thresholds. So there is a threshold. The threshold here is the sum of the masses because it's a process. You remember you have a condition everywhere is that the frequency is a sum of the external energy is a sum of frequencies. Don't even remember what it is. So it's like it's a physical process, physical or unphysical, depending on the masses. But the threshold is always the sum of the masses. In this case, they are equal to m, but otherwise it is m1 plus m2. So you have to check if you can have effects on the imaginary parts above some thresholds. And for example, in Lab 2 or many on LHC, what you study are processes like this. You have electron, positron, that gives a Z, and that then decays. You do not see Z, you check the decays. Could be electrons, muons, many more things. And in this process you have contributions from loop corrections, bubble diagrams. And above a certain threshold, the bubble diagram will know if these circulating particles are fake or not, because the imaginary part will change. So for example, in Lab 2, you got this kind of peak, and that what you have here is, okay, there is the Z0 peak. Let me get out because this app needs to be, this file needs to be saved before continuing. Let's check now. So here you saw this peak that allowed you to check the Z particle. Now, if you go above the peak, check this thing that you will find. This is there is a bifurcation here, and this corresponds to a process like that. And that means that you have a bubble with double plus, double minus, which creates a correction. Now, the correction knows also about the imaginary part, and the correction will be different if W were fake or not. So, because lab 2 didn't find any unexpected behavior, you can know that W plus and W minus are not fake. The measurement has to be precise enough, but it was. LHC is not that precise. LHC can reach many more energies, higher energies. But actually this is what you do, because you cannot observe these particles directly. They do not live enough to go into, to reach the detectors. So what you observe is their decay products. And since you do not observe them directly, you could see they could be fake. Well, actually there is a difference in fake, between fake or not, in the loop corrections because of the imaginary part. But let's check this kind of process. Let's assume that you have, this is a possible process involving the Higgs. The imaginary part will be different depending on whether it is fake, the Higgs field is fake or not. You can exclude that Z is fake. Same way as for the W's. But the point is that the threshold where the imaginary part changes is the sum 91 plus 125 GeV, and that was missed by lab 2 because lab 2 stopped here. At 216, you would see something similar like that, or with a different shape. But anyway, whatever you see, it would have a different shape depending on whether the Higgs field is fake or not. So there is where you can see. Now LHC can reach much higher energies, but it's not equally precise. So maybe the answer is already buried in the data of LHC, or maybe it will be discovered when a linear collider will be built. But anyway, it is there. So this is a possibility because it's not excluded today that Higgs could be a fake. So in gravity, we have a triplet. that is the metric, the scalar, and chi mu. And you can make loop calculations. Now you know how to compute loop calculations. And one thing that you can do when you resum, let's say you have a chi produced by something, then you have bubbles with anything inside, chi itself, phi, g mu nu, standard model field, and then you know that when you resum the bubbles, you get a corrected propagator. It's a Pauli fields propagator, but the only thing we are interested in is the overall pole, so the structure is not interesting for. So this goes into 1 divided by p squared minus m squared, let's say, plus a bubble diagram. Well, basically that means that you have a correction. The pole will be moved from its original position. You have a correction to the mass, let's say, on the new, so this is an approximation, around the new pole. You have a new mass, but you also have an imaginary part, and that defines what you call the width. And for example, you can compute the width of chi of this spin 2. So for example, you can compute the width of the muon with a standard model, and normally the reciprocal of the width is the lifetime. Well, if you do it for a fake particle with the minus sign in front of the propagator, you will find that this is negative. You have a negative width. And this takes you to one of the implications of the quantization prescription, which is the violation of microcausality. Which is actually the new understanding of space-time at small distances, or the new non-understanding of space-time, because basically at very small distances equal to the reciprocal of these masses. High energies, which means energy is larger than the fake mass, the mass of the phacon, or small distances, which means distances smaller than the reciprocal of the phacon mass, you will have there will be no meaning of time, present, past, and future will have no meaning. How do you see that? Well, we will discuss about it tomorrow, but basically if you take a bright Wigner and you compute the Fourier transform, you get you get something that this is the result for both signs of gamma, and if gamma, positive or negative gamma, give always a damping factor. So you don't have to worry that this blows up. It's not possible. It's a Fourier transform of a L1 function or L2 function. It has to be L2, can blow up, because there is a theta in front. But the theta reverses the sign of time. So that means that if gamma is negative, the theta will pick the future instead of the past. And that's why you violate causality, microcausality. Only for small distances when this oscillating factor does not kill everything, because otherwise it's averaged away to zero. So tomorrow we will discuss this in more detail, and we will also see that the violation of microcausality survives the classical limit. So even the classical limit will have some effects. It's not only just a quantum effect, but only at very, very small distances. It will not even depend on h bar. Okay, let's see. We will see on Thursday.